In this presentation, I will discuss the phenomenon of spectral sideband splitting that may appear in strongly dispersion oscillating fiber. This work is the result of a collaboration between four groups: the Laboratoire Interdisciplinaire Carnot de Bourgogne from the University of Burgundy in Dijon in France, with myself, Fang Feng, and Philippe Morin; the Femto ST Institute in Besançon in France, with Yanne Chembo. The fiber that we will use in the different experiment is provided by the Fiber Optic Research Center in Moscow, in Russia, and Stefan Wabnitz from the University of Brescia in Italy has been involved in the theoretical analysis of the different results. This talk will be organized as follows. As an introduction, I will recall what is modulation instability in dispersing oscillating fibers. Then I will present the phenomenon of spectral sideband splitting with simulation and experiment, and in the last part of this talk I will discuss the influence of the pump pulse shape, both with a theory, and I will propose an application to pulse doubling. So light, when it propagates in a single-mode fiber, can be modeled by the nonlinear Schrödinger equation that takes into account both the second-order dispersion and the nonlinearity. When propagating in a fiber with anomalous dispersion, modulation instability can develop. It leads to two symmetrical sidebands, and the maximum gain of the sideband is continuously increasing with the pump power. Regarding the frequency of the maximum of gain, it also increases with the pump power. Quite recently, a new kind of fiber with a dispersion oscillating parameters has appeared. This fiber is called dispersion oscillating fiber, DOF. And to characterize this fiber and the sinusoidal evolution of the longitudinal profile of dispersion, you need the average dispersion, the amplitude of the dispersion fluctuation, and the spatial period of the fluctuation. And what is interesting is that when you take into account this longitudinal evolution of the dispersion profile, a new kind of instability can appear. And this instability can be observed also in the regime of normal dispersion. In the previous case, with constant parameters, no modulation instability could develop in the regime of normal dispersion. So when you have a periodic modulation of your parameters, you can have a set of sidebands that appear. These sidebands are unequally spaced. They can be also called parametric resonance, and the central frequency of the sideband is predicted by this simple law. And what we can see is that contrary to the usual modulation instability, here the central frequency of the sideband decreases when you increase the pump power. And the parametric gain is given by this formula. Here this is the maximum of the gain in the sideband, and what we can note here, this is that a Bessel function is involved in this formula. That means that the gain will not continuously increase when you increase the peak power. So those two formulas just provide the central frequency of the sideband and the gain that is observed at this frequency. If you want to predict the whole gain sideband and its shape, then you will have to use simulation of the nonlinear Schrödinger equation, or a linear stability analysis that takes advantage of the Floquet approach. This is what we will use in the following of this talk. In this talk I will also base the experiment on a fiber that is a 400 meter long fiber with a spatial period of 20 meters and a nonlinear coefficient of 10 per watts per kilometer. The amplitude of the dispersion fluctuation is 2 picoseconds square per kilometer, and according to the pumping wavelength we will be able to change the average dispersion, and we will be able then to change the ratio between the amplitude of the fluctuation and the average value. And here, for a rather low value of this ratio, we can observe that we have the generation of the parametric resonance. This is the first quasi-phase match sideband, and here we have also observed the second QPM sideband. The other sidebands that we have here, they are linked to multiple forward mixing between the pump and the first QPM sidebands. Now, one question that arises, this is what happens when the fiber that we use has very strong dispersion oscillation. Typically, when the ratio beta 2 amplitude divided by beta 2 average is much above 1. This is what we will try to investigate in the following of this talk. So, if we use a linear stability analysis, what we can see, this is that the gain sideband split into several branches. Here we see that the first QPM sideband is divided into 4 different branches. And in fact, this splitting here does not violate the preceding law that I have mentioned. So if we compare the position of this branching with the prediction of the central frequency, we can see that we have still a pretty good agreement. And regarding the gain, this formula is very interesting, because what we can see, this is that for the points where we observe the splitting, in fact, the Bessel function that is linked to this first quasi-phase match sidebands equals 0. So the fact that the gain equals 0 leads to this sideband splitting. This is here one physical explanation of this splitting. So we have tried then to validate the existence of the different sidebands by using an experiment, and for this, this is the setup that we have implemented. We start from a continuous wave at 1550 nanometers. So here this is an experiment that is carried out at telecommunication wavelength. We then phase modulate this continuous wave in order to avoid Brillouin backscattering, and we use an intensity modulator to carve into the continuous wave and to generate 250 picosecond pulses. These pulses are then amplified to increase their peak power. An optical bandpass filter is used to remove the VAC, and after propagation in the VDOF, we record the resulting spectrum, and we obtain this kind of map. And what we can see here, this is that we clearly observe the different branches that are linked to the first quasi-phase match sidebands. So here we validate the existence of the different sub-branches and the splitting that occurs when we increase the pump power. Here we have more details regarding this splitting, and we see that we observe several branches that are linked to the first quasi-phase match sidebands. So we have used additional numerical simulation to validate this kind of spectrum and to be sure of the interpretation. Now, if we compare the prediction of the linear stability analysis based on the continuous wave and our experiment, we can notice one point. This is that in the linear stability analysis, the branch disappears after a given power. Each branch finally vanished. In our experiment, this is not the case, and we can see that the different branches do not vanish. And to explain this behavior, we have to take into account the finite temporal duration of the pump pulse. And this is what we have done, and we can compare here the spectrum that are obtained using a standard linear stability analysis based on the continuous wave, and the results that are obtained if we take into account the probability distribution function of the pump. And what we have done here is very simple. We have taken the spectrum that we obtained by the standard linear stability analysis, and we have whitened the result by the probability distribution function. And using this simple approach, we can see here that the different branches here do not vanish. So this is really linked to the temporal profiles of the pump. We do not have here a single power that is involved. We have here a distribution of the power of the pump. And we have tried to propose an application of this behavior by seeding using a very weak seed that is located in one branch of the QPM gain sideband, and we had a look on the evolution of this seed. The pump is here plotted in red, and what we can see this is that the seed is amplified and is transformed into a doublet of pulse. And we can understand the generation of this pulse doublet by looking at the evolution of the amplification factor according to the pump power. And we can see that here we have amplification only for a narrow range of pump, and here we will have amplification only in one part of the trailing edge of the pump and another part of the leading edge and another part in the trailing edge. And what is also very interesting is that by just changing the peak power of the pump, we will be able to change the delay between the two pulses of the doublet, and we will also change the temporal duration. We can see that we can change the delay by a factor of more than 2, and we can also here significantly change the temporal duration. To conclude this talk, we have shown that a spectral splitting of quasi-phase match gain sideband may occur in the regime of strong fluctuation of the dispersion. This splitting does not violate the existing analytical laws, and we have been able to confirm experimentally such a splitting. The details of the temporal intensity profile of the pump may significantly influence the output spectrum, and we have proposed a new scheme to obtain pulse doubling with a tunable delay between the two pulses of the doublet. So if you want more details on those different works, you can have a look on the following publication.